Hello, everybody. Thanks for joining me for this session about low latency GCs. My name is Jean-Philippe Bempel. I work for Criteo for 2 years now. And before that, I was working for a company in a financial domain. We were routing order to the market in less than 100 microseconds, so microseconds, not milliseconds. And at that level of performance, if we have a GC, even 20 or 30 millisecond GC, it's the kind of a thing. So we were kind of trying to avoid that. And when the Azul JVM thing was coming on with the C4 algorithm and reducing this poses, jumped in. It was in 2012. We were putting this JVM in production since then. And since then, I will try to work on those and to understand how it works and we achieve this low pose. So a quick show of hands: who had some GC pose issue? Yeah, so yeah, like more than half of the audience. Cool. So you're in the right place. So we will talk about this and how we achieve to reduce those poses, those reduce of the poses, or GC poses. We'll talk first with the concurrent marking because it's common for all the low latency GC, and then we will dig into the first algorithm, Shenandoah. It's not the first that came out on the JVM, but that's a new one from Red Hat. And then we will talk about the Azul C4. That's a big part because I have a lot of experience with this algorithm. And then the newbie, ZGC, that came from Oracle, open source then. And finally, we will help you to choose between the three of those algorithms. So concurrent marking. That's not new for new technology for concurrent marking. It's used already for CMS and G1 algorithm, and for all low latency GCs also. So the idea is to mark the whole object graph concurrently with the application. So your application is still running, and the algorithm is running in concurrently to mark all the object graph. It's based on the tricolor abstraction, and most of the time the snapshot, the beginning algorithm. So this abstraction is used by CMS, G1, and Shenandoah. For the rest, I will explain what's the difference. So let's take an example for concurrent marking. We have an object graph. So there is tricolor. So there will be three color: the white, gray, and black. At first, all the objects are white. The top left object is my GC root, and I will go through this object graph. And each time I visit an object, I'll change the color to gray, so I'm visiting the first object. And then from this object, I will go through all the children of this object, all the references, and visiting this object, so I mark it also gray. And once I've visited all the objects and all the children of the parent object, I will make it black, since I've done with this object and the children. And then recursively, I go through the object graph and go to the children of my next gray object, visit it, and then mark the parent object black, and so on, up until I've marked all my live graph object as black. The white object on the bottom is garbage. It references an object, but nobody references it. So this is garbage, and will be garbage collected. Okay, but it's cool with parallel GC, for example, with the stopping all the threads and doing this. But if you do a concurrent GC, there is some issues. So how we tackle those issues? First, the allocation. We can handle this by two ways for new allocation. So either we mark those objects automatically when we allocate an object, marking live. Either we are not considering the new allocation for the current GC cycle. So we make allocation into another region or other addresses special that say, okay, this is not considered by the current GC cycle. So we are not considering those or marking or whatever. And then the tricolor abstraction gives us two properties. So the mutator is the application thread. And so the mutator stores a reference to a white object into a black object. And if all paths from any gray object to a white object are destroyed, we can miss an object. So let's take an example to make it clear. We have an object graph, ABC, and we are currently marking this object graph. And we are concurrently executing this code into an application thread that modifies this object graph. So basically, the concurrent marking is at the B object currently. And we are referencing a white object from a black object. And we are destroying all the paths from a gray object to a white object. And in this situation, what I've got is I've lost the way to reach the C object. Okay, C object is considered as a garbage, but still it is referenced by the A object. So we have missed this. So how to resolve this? There is two ways, using the snapshot at the beginning algorithm or incremental update. We are currently dealing with snapshot at the beginning for ACTB then. And the way this algorithm is trying to resolve this issue is inserting a pre-write barrier. So it means that for every assignment that you make into your code, the JIT will insert new code to deal with this. So before each reference assignment, so if you have an X object that store into its F field a Y object, a reference to a Y object, there will be new code inserted by the JIT. This barrier will be active only when the concurrent marking. So there is a Boolean globally, a global state that will be tested before doing this. So that's the pseudocode of this pre-write barrier. So if the ACTB write barrier is active, then if the field that we will write is different from null, then we unqueue this reference into a queue that will be processed later. And this code is inserted for each write reference assignment. So, for example, you can see that this is the current JIT code emitted for this write barrier. So you have the first test, the two instructions are the test for if the ACTB write barrier is active or not. And then you have all the other tests. I will not go through all the instructions, but still there is an impact of your code just for dealing with the GC. So you need to be aware that there is some overhead of this, and it's not magic. We'll go to how to deal with this enqueue after for Shenandoah. So we'll switch to Shenandoah. That's the first low latency GC algorithm that we will see. It's coming from Red Hat. It's based on G1. And the project started in 2013. And this Shenandoah GC is non-generational. That's new for JVM GC because almost of the GC from the JVM are generational, but they choose to not be generational for that. There's still an option to do partial collection. Maybe they will consider in the future generational, but right now it's non-generational. Region-based. It's constant for all the low latency GC. They're all region-based, like a G1. They use a read barrier, also constant for all the low latency GC. For Shenandoah, right now, it's Brooks pointer. We'll see that this will be changing in the future. There is a self-healing concept that is also common for the three algorithms. The self-healing concept is the cooperation between the application thread, mutator thread, and the GC thread. For Shenandoah, it only happens for the concurrent compaction, for this phase only. Most of the Shenandoah GC is based on G1. just the concurrent compaction that changed because the G1 it's a stop of the world compaction, and for Shenandoah it will be concurrent. That's a tricky things to do. So, well, what are the phases for Shenandoah? First, there is the initial marking, stop the world, like for CMS or G1. Then you have the concurrent marking that we have explained before. Then the final remark that will sync what was going on during the concurrent marking, because we have the object graph that was changed during this concurrent marking phases. We need to catch up. So, for example, DQ from the ACTBQ, all the references that we have changed during this concurrent marking. So we need to catch up and process those references and to make sure that we don't miss any object from this operation. Then we have the cleanup phase, just a quick phase that is done concurrently. If there is some region, like the G1 region, that are completely with dead object or free, you can reclaim it right now for reuse and for new allocation. Then we have the tricky phase, the concurrent evacuation. So we're evacuating objects like G1 to free some regions, doing this concurrently. And then, as we have moved object, we need to update the references that point to the old location of the object to the new location. So we will need to update all the references that have been moved. So there is a phase with stop the world, and then the phase concurrently, and a sync up at the end. And then again, a cleanup phase where we can reclaim, once all the references were updated, we can reclaim those regions to do some new allocation in it. So let's focus on the concurrent evacuation. The principles are the same as G1. So we build the collection set with the garbage first. So we sort all the regions and say, okay, these first regions, there is mostly dead objects, some couple of live objects, but so few, so we can do get some region with a smaller of effort. And we evacuate those regions into a new region and release to reuse. This concurrent evacuation is done with the help of one read barrier, the Brooks pointer, and also 4 write barriers. So those 4 write barriers are additional to the pre-write barrier for ACT that we saw previously. So those barriers help to keep the two-space invariant. It means that all writes that need to be done into an object, if this object is in the from region, from space, it's not good. It needs to be on the to space. So you can't write into an object that is in the from space before evacuation. You need to write into the object that is in to space, the region, the destination. So Brooks pointer. What is a Brooks pointer? So all objects have in the JVM an additional forwarding pointer placed before the regular object. So you have this object with a header, that's normal for JVM, but with Brooks pointer we add an additional pointer on top of that that point to the object most of the time. So each time you need to access this object, you need to dereference this forwarding pointer to get into the real object for each access. So it means that we have a memory footprint overhead and also a throughput overhead with this. That's the kind of read barrier that is emitted by the JIT. So each time we have the address of this subject is here in the R12 plus R14 times 8, and then we go to the Brooks pointer by subtracting the address of the 8 bytes to get to the pointer, and we have the square bracket to dereference and to get into R13 register the real address of the object. So, how the concurrent evacuation is done by the GC thread. So we have an object that is in a from space region, and we need to evacuate to the to space. So the GC thread comes and go to this object, copy the object into the to space, and update the Brooks pointer so that all the old references that pointing to the object in the from space will be redirected to the to space object. That's fine. Now we deal with some application thread that want to read during the concurrent evacuation into the object in the from space. So those reader threads come and try to read into this object. They go through the box pointer and reach the object. As we don't write into the object, this is fine. We can read into the object. We are not breaking the invariant from Shenandoah. But then if we have writer thread, if you have application that want to write into the field of the object, could be like two writer threads, and it could be like two fields, different fields from the object. That's fine. But then we will break the invariant, so we need to deal with that. So for deal with that, we have each of the writer threads will copy the object on two different places in the to space, and then concurrently they will try to update the Brooks pointer with a CAS operation, a compare and swap operation, and one will fail and one will succeed. The one will fail will detect there is a failure on updating this Brooks pointer and reread the Brooks pointer to see if there is the new location of the Brooks pointer and follow it. It will discard the object and go through this new Brooks pointer to write the real value of into the object. So the write barriers. Any write, even primitive, that need to be done into an object need to be checked against the write barrier if we are breaking or not the invariant. So we need to protect the write into the from space from an object. So this is the pseudocode. We need to check if we have evacuation progress, if the object is in collection set, and if the object was not copied yet. And then if those three conditions are okay, we can evacuate the object. So this is a barrier that will be inserted for any write into this object. So we have this also code emitted for each write. So we're testing each time if we have the flag for evacuation progress, the other test, even the call to a subroutine. So again, it's not magic. There is some additional overhead for doing this and dealing with those corner cases. We have also 3 more exotic barriers to deal with the pointer comparison. That's something that is not very, very common in Java. The CAS operation, the compare and swap operation, and also for the clone. With this algorithm, we will see with the phases, there is like a late memory release. So to get those memory free and to reuse for a new allocation, you need to wait the end of the phases, basically, and all the update of the references. So at some point, you can have some situation where the allocation can overrun the GC. We have more allocation that the GC capable to release the region. To deal with that, there is 3 failure mode. One is the pacing. So basically, we are inserting a thread.sleep into the allocator, the application that allocates a lot. So we are pasting this thread. The second mode is a degenerated GC. So if during the phase of the Shenandoah we have detecting this overrun, we'll go into the stop of the world phase and continue the cycle of the Shenandoah GC. And then the last mode is going to a full parallel GC. That's the classic one. After that, since JDK 13, there is notable changes introduced in Shenandoah GC. Very important changes because they get rid of the Brooks pointer. They introduced this load reference barrier. This new barrier is a Baker's star barrier. It's like the opposite side of a Brooks pointer. It's for dealing with relocation. And it's evaluated not at the reference time, but at load time, when we load the reference. So with this comes the consequence that we can eliminate also the forwarding pointer because we are not using the Brooks pointer, so we can eliminate this Brooks pointer and put into the mark word the information to where the object were relocated, because we need this information. If we reach an object from a reference that was evacuated, we need to know where to look at the new object, the new location of this object. So we store this information into the mark word, and we can remove this Brooks pointer. So Roman Kenke, that is the lead project for Shenandoah GC, say, okay, those changes are so big that we can rename the Shenandoah GC to 2.0 for the next version, in fact. And there is some, I think it's done now, there is a backport to the JDK 8. So that's the good for the build from Red Hat. So that's also good news. So it's still evolving, this algorithm. So basically what we have explained for Brooks pointer, now you can trash those explanations because it was changed recently. Now we have done with Shenandoah, we can go to Azul C4. So when I heard about C4, the first thing that comes into my mind is this. That's because my dad was in the military. So, but in fact, I was heard that this C4 is also because they're doing also for the region this evacuation of the region, and so they are blowing away those regions like an explosive. So that's what came for the name, but in fact, officially it stands for Continuously Concurrent Compacting Collector, the 4C. It's a generational GC, so this is the same algorithm for young and old generation. It's also region-based, where they call it pages, but that's the same concept. They use a read barrier also. That's also constant for all the latency GC. But this read barrier is a loaded value barrier. I will explain later what is it. This comes with also the self-healing concept, comparison between application thread and GC thread again. They published a paper of this algorithm, the pause-less algorithm, in 2005. It really pause-less in the algorithm, but the implementation in a hotspot requires save point. Save point is when you stop all the threads to do some stuff because all the application threads are stopped. So there is still stopped overall phases, but very, very small, like for Shenandoah. For my experience of this algorithm, I've witnessed that the pauses most of the time are less than 1 millisecond. So the LVB stands for Loaded Value Barrier. It's a Baker's style based barrier. It means that we are, when we move object through the forwarding addresses, those addresses are stored into a table that is of heap at the side, not into each object like Shenandoah. And we apply this barrier at load time. Contrary to the Brooks pointer, it's at the reference time. It's like the new Shenandoah 2.0. It's at load time. And also the thing it's very new also is that they fuse into this barrier the marking state and the relocation state, as Shenandoah is just using this for the relocation. This LVB is ensuring that the C4 invariants are not broken for each access of those references. The invariants are the mark-through for the current cycle. So when we load a reference, we check if this object, as we load a reference, this object is live. So we need to check if this is marked or not by the current GC cycle. And if this object is not relocated. So if not relocated, we'll move it. So if the application checks this and this is not correct, there is a self-healing process that will trigger and to correct it, either to mark the object or to relocate and correct the reference. So the next time we load this reference, it will be correct and there is like no overhead to execute to access the object correctly. So this reference is checked at load time. It helps the JIT to optimize it, because if you have, for example, into a method a lot of access to the field of an object, you can hoist the access of this reference into a register and do the LBB, and then for each other accesses it will be okay. There is no penalty to access the other fields and executing the LBB for each access. So it's nice for the JIT to optimize this. The state of the objects are stored into reference addresses. They call it we call it for coord pointer for the GC. So we store into the reference addresses because it's only for 64 bits, and the address used are mostly like 42, 44, 45 bits only for addressing the heap. So we have plenty of bits that are left unused, and we can store some information into those reference addresses. So the LBB store the states into this. So they store an empty bit, so not marked through, so if the object is marked or not, and if this object is remapped or not, and the generation young or old. And then when we access the object, we check against a global state, expected state of the object against the address into the reference addresses. This state is stored either on the thread local or into a register. So the first version of C4 store this information in thread local, and then they change this to use a register, a dedicated register. So the thread local is almost L1 hit guarantee, but still this is a memory access. So if you dedicate a register, it will be faster. But you dedicate a register, so you may have some also overhead with the JIT compilation. But still, with our test, it's a win to use the register. So with the register, you have this code emitted by the JIT for each loading of the reference. So we're just testing the address of the object against R9, that is the global state, what is expected by the GC for this object, and then if this is not good, we jump to a slow path, or we just accessing the field of the object. As we store state into the reference object, we cannot use the reference as is, because there is some information, additional information into the address. So we need to unmask this address to get to the real address of the object. For C4, they use a kernel module, a special kernel module installed with the JVM that's doing the aliasing, because it's dealing with the memory directly into the kernel module. So they do all the mapping and allocation into at this level, so they can do the aliasing of the addresses of the mapping of virtual addresses and physical addresses at this level. They have also another mode without the Linux kernel module that use the memfd API. that's doing a multi-mapping. So multi-mapping we will explain with ZGC. Before going further, I would like to remind you the difference between virtual memory and physical memory and what we can do with that. We have virtual memory that's 0 to 2 power of 64, so it's very, 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 very large. And we have physical memory, like 2 to the power of 37, I think it's 32 gigabytes basically. So that's common hardware that we have. It's very, very short compared to, it's not at scale. So we can allocate a physical memory, a physical page that will be mapped into virtual memory. We can allocate another page also backed by another virtual memory page, but we can also allocate a virtual page that will be backed by the same physical page that another page in virtual memory. That's a cool trick that we can use. And we can have a virtual page that is allocated but not backed by physical memory. So in this case, if we access these memory pages, they will trigger a page fault, and the OS can do something to handle this case. This is the way the swap is implemented. So if we access these virtual pages, it will go through the disk and load this page into the physical memory and back to this virtual page by this loading of memory. Okay, move on. The C4 phases. Sorry. So we have the mark phase, that's marking all objects of the graph. Okay. Relocation, we are moving objects from one page to another to release the pages for new location. And the remap, that will fix up the reference graph to point into the new location of the object. As we're traversing again the object graph for the fix-up, for the remap phase, we can fold this cycle with this phase to the next cycle for the marking. So basically with this scheme, we have the 3 phases, and the last phase is followed with the next cycle for the marking. So as we're marking, we traverse the whole object graph. We can fix the reference and mark the object that we traverse, because here they are live, for the next cycle. So we have a gain into the process. So the mark phase, it's not the classic concurrent marking that we have. It's a precise wavefront marking. So it's a big word to say, okay, that's like a parallel GC. They do the marking through all the object graph. Like if there is no modification of the object graph. So it's the benefits of this, it's single pass. There is no catch-up or final remark that doing this. And still there is the self-healing process that will, if an application try to access an object that is not marked, it will mark this object. So we will fix up as we go. So how it works? We have this example that we saw previously. We are in the middle of the marking as a B object. We have this application that change the reference in the process. So as we load the reference C here, we are triggering the LVB. And the LVB, we check if this C object is marked. So as it is not marked, we are marking this object. So we are helping the marking algorithm and see, okay, this C object, we are visiting it. So we are marking it as gray. And then we can save the world by marking all objects like this. So we can use a classical algorithm as we have no concurrency, and then we have the LVB. It will help to mark all objects correctly and precisely. That's a nice benefit of the LVB. So for the relocation phase, we select the page with the greatest number of dead objects, like the G1 garbage first. And we protect the page that we want to evacuate. So the protection is logically from the mutator threads. And we move object to the new allocated page. We build a side arrays of heap with the forwarding information, so we can store where the new objects are located. And again, the self-healing process can trigger when an application thread tries to access those objects. LBB will be triggered and copy the object to the new location and correct the reference with the new forwarding pointer. So let's recap with a schema to explain all of this. So we have 2 pages. We have distinction with virtual and physical memory. We have allocated a new page to move object into these new pages. We protect the page that we want to evacuate virtually. And we move object from this page protected to the new page allocated. We install the forwarding table as if there is an application thread that tries to access this object, they know where are located now. We can release physically the page before. So virtually it's still allocated, but physically we can now release this page to be reused. As we have protected the virtual page, if there is access to this page, it will trigger the LBB, use the forwarding table, and go to the right location. So we can allocate a new page in the virtual space and back this page by the previously released physical page. So as this algorithm is going on, we can have a situation where we're reaching the limit of the memory, but as long as we have only one page free to start the process, we can releasing pages as we go on and go through the process and catch up and to release pages and use those pages for the new allocations. So this algorithm is catch up really quickly for a very application thread that's allocating a lot. For the remap phase, very classic, and we traverse the object graph, we fix up the references. For each object, we're executing the LBB to correct the reference. If the application thread in the middle is trying to access, we fix up also the reference using the forwarding information. And as we traverse again, we mark in the same time the object for the next phase. So at Criteo, we are using C4. Why? Because we have a Hadoop cluster, a big Hadoop cluster, like 2,000 nodes for this Hadoop cluster. And this architecture have kind of a bottleneck. They are using a name node for storing the metadata of all the files that are spread into the nodes. And as we have a lot of nodes, we have a lot of files, and we have a lot of metadata that need to be stored into this name node. So we have a name node with a heap, one JVM and one heap of 580 gigabytes. And as we are using the OpenJDK 8, we are using the G1 GC. But it tends to be very hard to tune because as we have a lot of object allocating, storing for a long time period and then garbage, we reach a point where there is fragmentation into the G1 and fall back to a full GC. So as we are using OpenJDK 8, full GC for G1 is single-threaded. So you can imagine that with a heap like 580 gigabytes, it takes like 30 minutes to do the full GC. So that's an issue. So we have tested C4 for this case, and it works very well. So we put into production since October 2017, and since then, no issue regarding the GC with this. So it's working like a charm. So finally, the GC. So we have 10 minutes left, but for the GC, we'll be very quick. Anyway, so the GC is non-generational, like Shenandoah, but they're planning to do a generational version. It's region-based. Okay. So the region are called ZPGs. They are dynamically sized, but that's a constant for all the latency GC. So ZGC is doing the concurrent marking, concurrent compaction, but also the concurrent ref processing. Ref processing is for the weak ref, phantom, finalizer, and soft reference. So usually the classic GC doing this under the stop of the world phase. Here ZGC is doing this concurrently. They use the color pointer like C4, so they stored information to the reference address and use the read barrier. This is the read barrier. They are using a thread local one in the current version. So they are using the R11 register as the address for the thread local, and they reference the field to access it. So this is a memory access, and then this is basically the R15 is the thread local and the test instruction against the R10 that is the address of the object. So this is very similar to C4 but on thread local. Again, the self-healing process. So we are familiar with this now. Since it's in the OpenJDK since the JDK 11, still under experimental. And for the rest, so Click was the architect of the C2 JIT compiler at Sun, and then works for Azul for like a decade. So he knows a lot of about C4. And when you look at the ZGC, you say, whoa, that's very similar to C4. GPGC is a generational poseless GC. It's another name for C4, done by Oracle. And that's completely true. That's the main idea, the same concept, the same algorithm. So basically, you take C4 and you get what the ZGC is doing, with just small details on difference. Just the naming of the phases are different. So we have still the initial marking, concurrent mark that is followed with remap, a final mark to catch up some other things. The prepare for relocation, this is the phase where, for example, they do the ref processing. They stop for relocate and they do the relocation concurrently, and then we are looping to initial mark because the remap phase is done with the same the next phase, the concurrent marking. So we have this color pointer where we store metadata in the reference address. For up to JDK 12, they are using 42 bits to address the if, so 4 terabyte max. And then since JDK 13, they are using 44 bits and 16 terabytes. Sorry. So they are using 4 bits to store the metadata inside the reference address. For those metadata are marked 0 or mark 1, so marking depending on the GC cycle, if the object is remapped or it's finalizable. So we have this nice schema inside the source of the GC that show you that for 42 bits, we are still a lot of 0 at the end of the address of 64 bits that we can use. So currently they are not used. Only the 4 bits here are used after the 42 bits. And then to unmask those color pointer, they are using a method called multi-mapping to unmask when they're fronting. But some hardware have the support built inside the instructions. So, for example, Spark or ARM, we can unmask directly the address by the CPU. But for x86, there is an overhead for those for doing this. So the trick is to use the multi-mapping, as there is only one view active at any point. We can do this, and because we have plenty of virtual space, like 64 bits addressing is very, very, very large. So we can use this space for other things. So to explain, we have one page backed by a virtual memory. One virtual page backed by a physical memory, and we have one kind of address with the mark 01 bit set, and then we can have another virtual page with the other metadata bit for the other address, and another one, and the three view will be backed by the same physical page. So as we go to the GC cycle, we will change the metadata bit, but still we are accessing the same physical page and the same information. We are just changing the view of this and the addressing. So we not have to unmask those metadata as we're changing the view, and we're still accessing the same information. If you are using ZGC for containers, be aware, because of this multi-mapping, the way the Linux kernel see the memory used is triple. So as you have 16 gigabytes of heap, you have, from the kernel perspective on RSS, 50 gigabytes. So if you put your memory limit or your container a little bit too tight, you may have some issues. That's an email from Alexis Shipilef that tested the ZGC and see that there is some reporting from the Linux kernel that is not in adequation with what is really used physically. So be aware of this. Otherwise, that's similar to C4. What's the difference? The way that we are unmasking the ref addresses. For C4, they are using kernel module, or sometimes the same multi-mapping than ZGC, and ZGC is using only multi-mapping, or maybe the hardware support for other platforms. For page and relocation, C4 uses pages that are fixed, 2 megabytes, and for relocation of large objects, they are not moving they are moving those large objects by remapping. So they are just using the unmapping and remapping by virtual pages to do this relocation. For the GC, the pages are dynamic and up to 100 megabytes large. And for large objects, they are not moving it like the Among Us object for G1. So with this, how to choose between those GC algorithms? If you want to run this on Windows, you have only one choice, Shenandoah, that's supporting Windows. If you want a battlefield-tested GC, choose C4 or Shenandoah. The GC is still in early stages. If you want to minimize other kind of JVM poses, like ref processing or other things, you can use C4 that also implement this, or Z. If you don't want to pay for it, Shenandoah and Z, because C4 is a commercial product. With the slides that I will tweet just after the session, there is some references about the GC basics, or about the Shenandoah, about the C4 with the published algorithm, and the ZGC, of course. And with this, I have finished for this session. So this is my Twitter. I will send a tweet with the slide to have the reference and to go further of those algorithms. Thank you.